So, hi everyone. My name is Pekan Gupta, and I'm from Smart Modeler. Smart Modeler is in the business of memory DIMMs and SSDs, and we have been making something else as well, which is persistent memory. Though it's a different kind of persistent memory, NVDIMMs-Ns, slightly different from Optanes. And my talk today is future of persistent memory in different form factors and architectures, especially what comes with CXL. During the FMS last month, we heard a news about Intel killing of Optane, which is somewhat anticipated, but the persistent memory over here is the concept, and Optane is an implementation. So my whole discussion over here is what happens to the concept or the technology itself, the persistent memory technology, when it migrates to CXL. What are the changes in the form factors, architectures, and likewise. So before we start our presentation, there has been various discussions about use of persistent memory. And before me, Tom Collin, who was one of the presenters in last session or yesterday's morning session, gave a very nice talk of different medias being used behind a persistent memory as a technology. However, there is something which I want to cover on the use case as well. Why persistent memory is required in the system even today. It's not about caching, but it's more about high availability, which is very important. If you look at a general trend of how the system goes down and is recovered, it can be a system crash can happen because of any incident. It can be through a malicious hack or a network or a power outage, as shown over here, or it can be a buggy code or a misconfiguration. In today's world, we do a lot of configurations for different types of VMs and other use cases and stack, which can also lead to a system downtime. However, the overall goal of recovering the system and various stages is similar. You have to go through a detection phase, then a containment and recovery. So what happens during these phases? During a detection phase, you detect the failure, and the next and the most important part of your step is, or system admin struggle to do, is the containment. Containment means you are trying to reduce or contain the blast radius. It's a very important thing in today's data center, because with all the servers connected to each other, it's very easy that a fault in one of the servers can quickly affect the SLAs on other servers over here. And therefore, it's very important to contain the fault or contain the downtime. And this is where some of these techniques come into picture, which is like you try to roll back, which is go back to an older snapshot which was working if it was a misconfiguration. You try to diversify the load or distribute the load. So if there was a network outage, you try to route it through different switches. And the last one is activate the backup. In all of these containment use cases, you'll see there is a common picture. You need to be very fast. And that's where persistent memory comes into plays an important role, that if you have a snapshot which was already loaded into a persistent memory, you can quickly load it up. If there was a configuration which was already working, you can quickly load it and reload it back and make your system work again. Another important thing is if you had a backup, which was, or a data which was snapshot just recently, you can reload it or stage an active ongoing transactions. You do not want to roll back your transactions because that will affect everyone else behind you. So the best part is you stage your transactions intermediately and allow the system to recover. All this can happen if you have a substantial amount of persistent memory in your server or in your node, attached to your node. After the containment zone, the next step is usually the recovery. How do you do the recovery? You have to isolate the error, and also you have to figure out what caused the error. And this is where some real-time error logs and security logs are very helpful. This is where you actually try to figure out what really happened. What was the loophole which a hacker tried to exploit? Or what was the last stack command, a function call, which which cause the system to go down. And this is where the real-time logs are very helpful. Usually these logs are stored in SSDs, but then it takes, they may not be in real time or they not be to the last stack. If it's a persistent memory, yes, you can get a very active or a real-time log covering the last function call which caused a crash. Again, if your stage transactions were already transferred to the persistent memory, you can recommit them without rolling back. So this gives a way to continue your execution and that will contain your blast radius. The last and the important one is when you activate the backup can be in cold storage, which is very slow. So your persistent memory can act as a cache, which can be used to collate the backup from different sources, rebuild or recreate the data, and quickly bring it back to the online system. So this is where we see that persistent memory is a key component of a high available system. It helps not only in the containment zone, that means to contain the blast radius of the fault, but it also helps in recovery. So in general, persistent memory as a technology is here to stay. The difference is how it gets attached to the system. Let's look at how the persistent memory is attached to the system today. In current generation of CPUs or servers, you have two types of persistent memory. One, like an Intel Optane, which Intel recently announced that they will not be continuing the technology or supporting the technology going forward. And the other option was NVDIMM-Ns, which is more of a DDR4 type technology. Now, both these two technologies are directly connected to the CPU, which means they are sitting on a parallel bus. And one of the major disadvantage of having anything connected to a parallel bus or a directly attached CPU is you waste a CPU channel or a memory channel. So if this DIMM is running slower than rest of the DIMMs on a channel, it will slow down your processor bus and affect your performance. Second thing is, these are very critical slots. So you do not want to put a low density memory over here. You want to maximize your memory footprint. And this is the reason persistent memory as a technology was not very popular when it was connected only on the directly attached memory buses. With CXL, what it brings is you extend the memory channel on the serial attached interface. This is where new types of form factors are playing an important role. So persistent memory, which is maybe slightly slower or can have lower capacity, can be moved on a serial bus. This is where CXL comes into picture. So we'll talk more about the different form factors, but I would really like you to look at one of the videos from Gartner. It was shot in 2020. And this video talks about the use case of a persistent memory technology in an in-memory databases. It does not talk about what type of form factor to use. It just talks about the technology itself. So, continuing about the different form factors of persistent memory. We just saw that persistent memory can be in a DIMM-like form factor. This is where Intel Optane DIMMs and NVDIMMs have been there for some time. The biggest advantage is low latency. Anything you connect to a parallel bus will have a low latency and give you the best performance. But the challenge is you have to be dependent on platform, which is the CPU architecture itself. You cannot use your DDR4-based NVDIMMs or Optane DIMMs on DDR5-based CPU. You have to buy a new DIMMs. The second and the most important one is it will bring down the performance of the entire bus if it runs slower than the rest of the DIMMs. So again, Optane DIMMs, which use a different type of protocol and run slower than the standard DDR4 or DDR5, were not a good fit because they will bring down the performance of entire channel. The third and the important point is capacity. You can really not pack hundreds of GBs on NVDIMMs. The reason is, first, the PCB real estate is very small, and secondly, NVDIMM-like architecture requires external backup power. So that brings another challenge of putting a large capacity of memory in DIMM form factor. This brings us to another form factor called EDSFF or E1.S or E3.S kind of form factors. Yeah.
Well, of course, Optane doesn't need battery.
Yes, Optane does not need battery, but it comes with another challenge of bringing the performance down. True. I'll cover some of the architectures in the next slide, the difference between the two. So within the, if we compare the form factors, the second type of form factor is EDSFF form factors, which is sitting on a serial bus. And the advantage of that is they are platform agnostic. So they do not run DDR4 or they isolate or decouple the DDR4 or DDR5 or any media technology from the processor bus. So you can plug in any CXL-based device on any CPU which supports CXL. The important and the most, I would say, advantageous feature of this form factor is they are hot pluggable. Now, memory has still not been to a, it's difficult to isolate a memory region and then plug it out for serviceability. But at least this form factors support that kind of feature. So in tomorrow's world, if your memory module goes down or has bad regions, you do not need to shut down the entire server. You can just isolate that memory device, plug it out, and replace it with a good one. So that is a very important aspect of which improves the serviceability of memory DIMMs comes with EDSFF kind of form factor. However, some of the challenges remain like what they were in DIMM-like form factor, that capacity is limited by thermal and PCB constraints. So you do not have, these form factors are still smaller than what we'll see on the rightmost side, and the thermal budget is very limited, which is specified by the spec itself. So you really cannot pack a very high density or a capacity module unless it gives you a decent power budget on your, for I would say, watts per GB. The last and the most important form factor is PCIe kind of form factors. Now, the biggest advantage is same, or the top two advantages are almost the same. Like because it sits on the serial bus, it is platform agnostic or CPU agnostic. Any CPU which supports CXL can be used with this kind of a form factor. The other aspect is you get very high memory capacity. Why? This kind of form factor can support two types of implementations. The one which I showed is you can connect DIMMs, or you can have soldered down components on the board itself. So either way, you can get, because of the PCB real estate, you get enough room to pack in high density DRAMs on it.
Those Optane DIMMs on that?
Yes.
Is this a real thing? You actually have this?
Yes, Smart Modular developed this. It's called a Kestrel card. And this Kestrel card has 2 terabytes of Optane DIMM just on one single PCI slot. So before Intel announced this, we had developed it for a specific tier 1 hyperscaler. And that's the advantage. You can pack 2 terabytes of memory on a single PCI slot. So that proves a point that it can get to a very high memory capacity if designed rightly. Another important point which we miss while kind of comparing the technology is sourcing. So when you make a PCI form factor which allows DIMMs to be in a pluggable form, you can actually source this memory from any vendor. It may not be beneficial for everyone, but some of the big companies, they try to squeeze down their margin by either reusing their DIMMs from the previous generation or trying to bring down the cost by purchasing in bulk. And this is an important part of this form factor is it allows multi-sourcing of DIMMs and mixing of the technologies. So you get best dollar per GB benefit from this kind of a form factor. Again, the limitation is it's not hot pluggable, so the serviceability aspect is limited.
This is very interesting. So if you're saying you have the regular DIMMs, not non-volatile, just regular DIMMs, and, for example, Optane on there, somehow you have to know, maybe we're going to get to this, somehow you have to know which one is which, because they always say, oh, this is persistent, oh, it's not persistent. So your program has to know what the technology is, even if you can mix them, you have to have some way of identifying what it is. You don't know what
Yes, yes. And that's where the concept of fabric manager and comes into picture is the fabric manager is a layer of software which understands which memory region is persistent and which is not. So it will allocate you the region based on the attributes.
Does this allow you to plug Optane memory into AMD machines?
Yes, yes. We have tested it on AMD machines as well. We did test it on AMD and ARM as well, honestly. But the challenge is sourcing the Optane DIMMs if it's available today. So, talking about the form factors, the next shift is what about the architecture? And this is an important slide for talking about different types of architecture. You might have heard about NVDIMM-Ns, but I want to introduce two new things which were already spec'd out by JEDEC, but probably very seldomly used in the market or unavailable in the market. So those were NVDIMM-P and NVDIMM-F. So let me compare them side by side. What NVDIMM-N does is, if you get a transaction or a memory read or write from the host, a controller over here, it can be a CXL controller, directly dumps that read or write data into a DRAM. And if you get a read, it reads it back from the DRAM and gives you back. The persistence flavor is achieved by adding a non-volatile controller which senses that there is a power fault and it gets the energy from a battery backup power and backs up the data from the DRAM into a NAND flash. So an important part over here is the backup only happens when there is a power loss, not in active life. Therefore, in active life, all your data transfers happen on the DRAM, whether it's write or when it's a read, it is fetched from the DRAM back to the CPU host. So your capacity is actually based on amount of DRAM which is packed into your module. And the latency is also DRAM based. That means because you're hitting the DRAM, your data, active data is stored in the DRAM, you get the similar latency as a standard memory module, which is a low latency. When you compare this kind of an architecture where NAND flash or backup only happens during a power fault with something like NVDIMM-P, it's a little different. In this case, you really do not have any DRAM, but you have proprietary media like 3D Crosspoint, which is being used to read or write your data or actively store your data. So the capacity is dependent on the capacity of your media itself. Now, media can be 3D Crosspoint like, it can be different technology like MRAM. We have a gentleman over here who has given a very good talk on the NRAMs and any other similar media like phase change memories or ReRAMs. The advantage over here is you get the benefit of density probably, and you do not have to worry about the backup power, which is the batteries and the NAND flash and likewise. Everything is stored in the persistent media itself. The challenge is the latency and the endurance. The third architecture over here is something which we have seen in Flash Memory Summit. It's CXL-based SSDs. Now, if you compare, there was a similar technology like NVDIMM-F some time back. What this kind of an architecture does is it uses DRAMs as a buffer, not really as an active media. It uses DRAM as a buffer. So your data is actually buffered in the DRAM, but slowly is percolated back into the NAND flash or any other persistent media. So capacity is determined by this media, the NAND flash. So you will get a very high capacity when you go for a CXL-based SSD. The challenge is the latency, because NAND flash is very slow. So as long as you're hitting the DRAM buffer for writes and reads, your latency will be good. But as soon as you start hitting you get misses and you start hitting the DRAM, NAND flash as a media for your reads, your latency will be very slow or very large. And this is one of the challenges why NVDIMM-F was not very successful or did not really see the mainstream market, because if you put a very slow media or DIMM on a parallel bus, it's going to kill your performance of the entire channel and your server. But coming back to CXL, again, you are talking on a serial bus. So this kind of architecture may make sense, assuming there are some assumptions here. You have enough DRAM buffer. So you have to calculate the right amount of DRAM to NAND ratio for your application. It can be as close as 1:4 or 1:2 if you want to have a very low latency over here, but that will increase the cost. If you want to go with high capacity and you can live with a larger latency, it can be as much of as 1:8 ratio. That means for every gigabyte of NAND, every gigabyte of 1 GB of DRAM is to 8 GB of NAND. So 1:8 kind of a ratio. So let's talk about the different characteristics of this kind of an architecture, or the three architectures. Here on the left we have NVDIMM-N, which was DRAM-backed NAND. In the middle we have something like an Optane DIMM, which was non-volatile media-based persistent memory. You have MRAMs, RERAMs, phase-change memory, and NRAMs. And the third one was CXL-based SSDs, where DRAM was used just as a buffer, but actual data was stored in the NAND. So what are the common features? All are persistent. They all support memory semantics. The NVDIMMs definitely support memory semantics of load and store. We have seen Optane-based DIMMs support that. And even CXL-based SSDs will support that because they are using CXL.mem protocol to talk to the front-end bus. So they all support memory semantics. They all give you cache-level granular access. NVDIMMs do, and Optane DIMMs do, and even the CXL-based SSDs would do, because again, they are using CXL.mem, not NVMe. So these are the common features. But where they differ is the latency, capacity, reliability, and cost. And these are the 4 factors which will determine what type of memory architecture you would use. So if you look at the latency, NVDIMMs will give you a DRAM-like latency or a standard memory module-like latency because your active data is stored here. When you go to the phase-change memory-based or a persistent media-based implementations, it will give you a higher latency, but the latency is determined by the media itself. When you go to a CXL-based implementation, you will get DRAM-like latency only to the point when your accesses are hitting the DRAM buffer. But at a later point, you will get something like an SSD-like latency. So it's a very high latency. And this arrow definitely shows that point. With increasing capacity, you get increasing latency. That's the second point, which is the capacity. The NVDIMM capacity is limited by backup power. You need to have a backup power which is battery-based or supercap-based. So it's limiting the capacity, what you can hold here. The capacity of Optane DIMMs is really dependent on the media, and the capacity of CXL-based SSDs will be very high because it's using NAND Flash. So NAND Flash have probably 16 times more capacity than the standard DRAMs. So it will be very high. And the same thing determines the cost. The cost is driven by the BOM components. So NVDIMMs will have a higher cost. The center point, which is the Optane-based SSD implementations, will have moderate, and the CXL-based SSDs will have a lower cost. Again, it depends on the DRAM the ratio which you can pack in. The important aspect is the reliability, and this is something very important when you go to the memory side, because for a memory, even a small bit corruption or an uncorrectable error can actually bring down the entire system. This ties back to my first slide about bringing the system up and affecting the system down, what affects the system downtime in a general infrastructure. So if you look at the reliability aspect, the endurance of NVDIMS-N is really dependent on the DRAMs, which is theoretically infinite or practically very high, because the NAND is only used during the power fault. So you get very high reliability when you use NVDIMS-N. You get moderate or limited reliability based on your workload when you go to Optane DIMMs.
That's not my understanding, unless Intel has been lying about this. I have a bunch of Optane DIMMs I've been pounding on for a couple of years, and I have not had a single failure rate. Many terabytes to it, and they're still showing like 99% of the lifetime remaining. So that's one thing. You may know, I'm not saying you don't know more about it than I might. And then the other thing is the latency of DRAM. You have to add the CXL bus latency, which my understanding is that's close to 100 nanoseconds, 80 nanoseconds. So it can't really be less than 100 nanoseconds if it's big and you have to do a page.
Yep.
TLB miss, you're going to be more like 150 or 200 nanoseconds in that DRAM side.
So this latency I'm considering with the CXL control, ASIC-based CXL controller and DDR5. This is something which we have seen in our simulations with the standard memory module. Again, this number is based on the first bit of the first flip entering the CXL device itself and exiting the device. So it is just the device latency.
So it's writing.
Yes.
Okay, writing's going to be fast also. The
Yes.
SSD, you don't fill up the cache.
Exactly. Yes. So coming back to the reliability aspect, the reliability of NAND Flash or CXL-based SSDs will be low. And this is our current estimate because when you really write the NAND with smaller chunks of data, you actually increase the write amplification. And then folding and other weird leveling techniques, when they kick in, once you start filling up your NAND DRAM buffer, that's when the NAND flash behind this module will wear very fast than the standard SSDs. And therefore, the reliability aspect may go down, but again, we have to see the real performance benchmark as well as the real endurance numbers when these kind of devices come into the market. So this was a comparison of different types of memory architectures, persistent memory architectures, which are there in the market today. And I would just summarize by saying is, each one of them is good for their own characteristics. You have to really decide based on these characteristics and your workload, which one is really a good fit for you. If you want a lower latency and a high reliability, and you are ready to pay a cost for it or a dime for it, go with NVDIMM-Ns. If you are okay with high latency, but you want really low cost per GB or low cost per TB, then you may like CXL-based SSDs. And somewhere in between, the balance of both is these kind of devices which use persistent memory media like Intel Optanes and RAMs and likewise.
Also, one on the right guarantee persistence of your writes.
So in this case, what you do is you play with multi-level. So you have a small buffer, or I would say a small supercap, which will flush down the data into the NAND if you lose a fault. Second thing, and very important part, which comes with CXL is it implements something called the command sets, which will have global persistent flush GPF flows, which break the whole flushing of the buffer in two stages, GPF stage 1 and GPF stage 2. The stage 1 is when you actually flush the buffer, and that may give enough time for these buffers to percolate the data into or push the data into the NAND flash, because you are doing interleaving, multi-die plane interleaving over here. Second thing is you may have a smaller supercap. You cannot have a supercap over here because you have to flush out the whole DRAM into the NAND. So you have to have a battery backup. But here, the DRAM buffers are very small. So you can still live with a small or a whole time where your server provides enough power till it flushes the data to the NAND, or you can have a small super cap over here which allows you to flush the data in the NAND.
It's no different to power loss protection on SSDs today.
Yes. The difference would be the ratio. The higher the ratio, the better latency you get. But it increases the cost and it brings back to the point, it makes it as close as like this. So, to end or summarize my presentation, I would just leave you with these three takeaways. Is persistent memory as a technology is here to stay because it helps, or it's a key component in high available systems. Especially, it reduces the blast radius, as we have seen earlier, and it reduces the time to recovery. The second most important point which I want to bring to your attention is about the architectures. I showed three different types of architecture, and you have to really select the persistent memory architecture based on the latency, cost, and the capacity which fits your needs. And the last of all is, with CXL, the memory is moving on the serial side, which also gives a way of moving persistent memory on the serial bus. So there are different form factors like EDSFF and PCI Chem, which were not really used for persistent memory or memory technology as a till date, are now becoming as one of the important form factors for use cases of memory technology as a whole. So thank you. That was all from my side today. Any questions?
What's the availability of this? I mean, obviously you need a CXL motherboard. Are there any that you can plug that into? Is it possible to buy one of these or get a sample or something today?
So this is available today, but without CXL, because we do not have CXL today.
So
it's a standard PCI.
So you have all the delays of that.
Yes. Yes, but if you look at Intel's website, there is something called Agilex M development kit, and it has an FPGA instead of this beneath this heatsink. I'm not talking about this picture; it's a different picture, different board. But it allows you to use Optane DIMMs or plug in the memory behind an FPGA, and if you can plug in an Optane DIMM, it acts as a persistent memory-based PCI add-in card.
But still same speed issues.
No, that has the CXL over here.
But you still need a mother. You still need, I'm not seeing how you do this. Does it plug into a DIMM slot? Is that what you're saying?
Yes,
Okay.
yes, but it is much bigger in form factor because it's still a development board, not a real production vehicle. So you can play with it, but you may have to talk to Intel how to enable some of the modes there on that board. This is what Smart is developing as of today. Again, this is a non-volatile version of the memory module, which has a built-in power cell, or I would say it's a battery backup power, which allows you to which looks like this kind of an architecture. So, and this is what we already have in the market today. Anything? Yes.
How big of a battery is required for that one on the left in a typical configuration on your device? I mean, it seems like it's going to be motorcycle battery, something pretty beefy.
No. So there are two aspects of
I know it's a function of a million things, but typically, what kind of battery would it be?
I can say that we can fit that battery within this E3.S easily today. And the size of instead of the size of the battery, what other aspects which are critical in determining the battery or the choice of battery is current or the amount of current which is being sourced when the power goes off. So what we do is, in this implementation, we try to shut off as many domains which are unused to save the power and lengthen the time of the battery use case. Second thing is the temperature. Batteries do not do well in high temperature. And therefore, it's very important to choose a battery which has high temperature gradient or can have a high life in a heated environment like a server. Therefore, in this case, in the new form factors like EDSFF, you have actually a better airflow because these systems, this kind of device is plugged on the front end of the chassis, and you get a cool air right from the, yes, like an SSD. So battery over here is preferable than putting a battery next to a DIMM or inside the chassis.
What's the capacity? What's the maximum capacity of that middle one there?
This one? The first prototypes, I think we are building with 32 GB, but we can scale to 64 GB per module. And again, the limitation is not the battery, because the batteries which we put can source only that much amount of sufficient current that we can back up 64 GB from DRAM to this NAND flash.
Do I have the ability to lie to the CXL controller? Can I tell it power's gone away, you need to flush the DRAM to the vault?
Yes.
So I could run on a UPC
Yes.
where I can have my motorcycle battery.
Yes. Exactly. Exactly. And that brings back to the point over here is when you have this kind of an implementation, you really do not need a supercap. If you can live with the, so these two implementations, you can have a power coming from the host, which is what you suggested, or a power which is built into the module. So either way, the power, when it's provided by the host, we call it as hold-up time. So if you have a sufficient hold-up time where you can provide the power, enough power, so that the DRAM content can be back to the flash, or in this case, percolated to the NAND, it will live. Okay, if there are no more questions, thank you.